Well, all the energy in the climate system ultimately comes from the sun. Fusion energy in the sun generates incredibly hot temperatures, millions of degrees, and so the sun radiates at visible, what we call visible wavelengths. So these are the wavelengths we can see with our eyes. And that energy, the atmosphere is largely transparent to that kind of energy. So it passes through the atmosphere unimpeded and warms the Earth's surface. Some of it is reflected away by clouds, but most of it reaches the surface. So the Earth has to get rid of this energy. You can't have an imbalance between incoming and outgoing energy for long. But the Earth, of course, being far away from the sun, is much cooler than the sun, just as well. And as a result, the Earth can't radiate the energy in these very short wavelengths. It has to use much gentler, long wavelengths, which we call infrared radiation. And you can actually feel this infrared radiation. If you go outside on a cold night, you can actually, on a cold night in the winter, then you can actually, and hold your hand up, you can actually feel the top of your hand feels colder than the bottom because you're actually feeling the flux of infrared radiation escaping from the Earth. Now, the reason I had to say a cold night in the winter, because those are some of the few conditions in which you actually do get radiation escaping from the surface of the Earth directly. On most days, under most conditions, the atmosphere is far too thick, far too opaque for this infrared radiation to escape directly to space. The atmosphere looks completely different in the infrared. If we were wearing goggles which only allowed us to see in the wavelengths that the Earth uses to shed energy to space, we wouldn't be able to see very far. We'd barely be able to see 200 yards to the college over there. So what the atmosphere does in order to get rid of this energy, it can't radiate directly to space. Instead, other mechanisms, clouds carrying energy up through the atmosphere, thermals, water vapor evaporating at the surface, water evaporating at the surface and then condensing at high altitude, forming rain, but releasing the heat which it carries at high altitude. And that's how the energy gets up through this fog of greenhouse gases. And so, as you're going up in a balloon, you're in effect rising through the mist and escaping slowly from the greenhouse blanket that envelops the surface of the Earth. And when you get to around 5,000 meters, you've reached that critical altitude where energy can begin to escape to space. Now, what happens when we raise greenhouse gas levels? You make this fog thicker and the mist rises slightly to envelop you. If you're sitting at a fixed level at 5,000 meters, the mist of greenhouse gas levels is rising, and where you are, energy can no longer escape space. You have to go a little bit higher for the energy to escape to space. And as every school kid knows, the higher you go in the atmosphere, the colder it gets. So that colder air radiates less efficiently, it loses heat to space less efficiently. And so if you go higher, the air is radiating less energy to space, and we have an imbalance between the incoming energy from the sun and the outgoing energy from the Earth. And that imbalance cannot survive, as I say, for more than a very short time. The Earth has to re-equilibrate. And what does it do? It warms up.